Welcome to Undamped free spring mass systems. So recall, a spring mass system is modeled by the equation my double prime plus cy prime plus ky equals f, where m is the mass, c is the damping coefficient, k is the spring constant, and F is our external force. Also recall that K satisfies the equation mg is equal to K times delta lowercase l. Here, delta L is the equilibrium stretch from natural length. So initially, or for now, we are going to focus on undamped systems, and we'll start off with undamped free systems. So in an undamped system, there is no damping force. So essentially there's no resistance just to motion in general. So there is no damping force. So we take C to be 0. And in a free system, there is no external force. And so in this case, our F is just identically 0. So what this leaves us then is we get a much simpler differential equation. So in an undamped or an undamped free system, is modeled by the much simpler differential equation, my double prime plus k times y is equal to 0. Or y double prime plus k over m times y equals 0. So let's look at an example. Let's say an object stretches a spring by 9.8 centimeters in equilibrium. And suppose the object is initially displaced 5 centimeters below equilibrium and is given a downward velocity of 0.5 meters per second. Our job is to find the displacement of the object for t greater than 0. So essentially what we have our natural length of our spring, and then if we add on the mass and have it hang at equilibrium, this distance between natural length and equilibrium, where our delta little L is 9.8 centimeters, or 0.098 meters. And then our initial condition, we're taking that spring, stretching it in another 5 centimeters from there. So this is our initial condition. So we're taking it another 5 centimeters beyond equilibrium because we're pulling it downward. In these diagrams, we are assuming the upward direction is positive. So this downward displacement, we are assuming that y of 0 is -5 centimeters, or in meters, -0.05 meters. And then it's given a downward velocity of 0.5 meters per second. So we have a downward velocity, y prime of 0. We're going down, so it should be negative. And then 0.5 meters per second. So this is the situation we're dealing with. And this is enough information for us to do the entire problem. So we have the equation y double prime plus k over m times y is equal to 0, with the initial conditions, y of 0 is -0.05, and y prime of 0 is -0.5. You want to make sure that all of your units match. So since our velocity was given in meters per second, and usually we work with meters per second squared for our acceleration due to gravity. If we're in metric system, it makes sense to go to meters. So at this point, we simply need to know k over m. So to find k over m, we'll use the fact that m times g is equal to k times our initial equilibrium stretch, or a stretch to get to equilibrium. So, and that what that means then is we have k over m should equal the equilibrium stretch divided by our acceleration due to gravity. Sorry, that's backwards. K over m should equal our acceleration due to gravity divided by our equilibrium stretch. So we have k over m is equal to 9.8 meters per second squared divided by 0.098 meters, right? And so putting this all together, we get that k over m should simply be 100. So we are actually solving that our IVP is now y double prime plus 100 times y is equal to 0, with y of 0 is -0.05, and y prime of 0 is -0.5. So if we're in an undamped free system, it actually doesn't matter what the mass is, other than that kind of, the mass will determine how long our equilibrium stretches. But as long as we're already told our equilibrium stretch, we do not need to actually know the mass of our object to solve our IVP or to create the IVP. So from here, now we'll go ahead and solve the IVP. So I picked my initial stretch of 9.8 centimeters just to make it so this IVP has very nice round answers. So we have our characteristic equation. R squared plus 100 is equal to 0. And this therefore means that R squared is negative 100. And so we get that R is plus or minus 10I. So this means then that our general solution should take the form y is equal to C1 cosine of 10t plus C2 sine of 10t. And then we can plug in our initial conditions and solve. So plugging in the initial conditions, we had y of 0 was negative 0.05, and y prime of 0 is negative 0.5. So if we plug in just that first condition, y of 0 would be C1 times cosine of 0 plus C2 times sine of 0. And this should equal negative 0.05. So we have C1 is equal to negative 0.05. If we look at y prime of t should be equal to negative 10 C1 times sine of 10t plus 10 C2 times cosine of 10t. And if we plug in y prime of 0, we are looking at negative 10 C1 times sine of 0 plus 10 C2 times cosine of 0. And that should equal negative 0.5. So sine is 0, we are just looking at 10 C2 is equal to negative 0.5. We actually wind up getting that C2 is also negative 0.05. And we get as our final solution that y of t is equal to negative 0.05 times cosine of 10t minus 0.05 times sine of 10t. So as a general rule, undamped free systems have a fairly simple general solution. If it's not as pretty as this one, it may have square roots involved, but it'll just be a cosine something t plus, or a C1 cosine something t plus a C2 sine something t. So in the next video, we'll go ahead and look at the general case and talk about kind of how we can interpret our solution.